Well, let's talk about the answer key to our workbook this week. In part A, a cart of mass M is attached to an ideal spring that can stretch and compress equally well. Ha ha. The cart and the spring rest on a smooth horizontal track. The cart is pulled to position A, stretched, and released, and then it moves towards position E, where it's going to get squished. Show with the sketch of a position diagram how the velocity of the cart changes between the points. So basically what they're showing here with this diagram is that we are getting farther and farther. So basically they're showing acceleration, that the cart accelerates to point C, and then at point C, the spring starts to squish, so the cart slows down. So that's what the dots are showing us, that the speeding up, and then the slowing down, it's showing our position changing. Here are some free body diagrams for the different locations. So you can see that the spring force is largest when we're at the ends because the spring is all the way stretched out and it's pulling it. When it's all the way stretched out, it's pulling it to make it smaller. And when it's all the way squished, it's pushing it to make it larger. At the intermediate positions, the spring is smaller. Right when we're at position C, when the spring is neither stretched or compressed, then the there is no force on the spring because it's not being pushed or pulled. At that point, you can see at every location the normal force and the force of gravity are equal because we're not moving up and down. So we're just looking at, there's really no way to tell whether it's moving left or right based on the free body diagram. In every case, whatever position we're at, the free body diagram looks the same. Whether we're moving left or right. And the free body diagram does not indicate whether it's moving left or right. It just tells you which way the spring is pushing. The spring is restoring force, and it's always trying to push the cart in the opposite direction to what it's going. So what is the direction of the net force exerted by the spring? So you can just look at the little arrows and fill the boxes in. The direction of net force is right because the arrow is pointing right, left because it's pointing left. Direction of displacement from equilibrium is when the force is pushing it right, the displacement is left. It's to the left. All right, here's part B. Here's our energy sketches. So what's happening here? The M is it's stretching and it's on a ramp. And the natural length of the spring without the cart is at point E, so it's stretched all the time. And it's pulled to A, and now it's going to move up and down the ramp, up to point E, where it reverses direction and returns again. So the natural length of the spring without the cart is at point E. And so at point A, it's all spring energy, right? The spring is all the way stretched out right here. Then as we move up the ramp, we have turned some of our spring energy into kinetic energy and gravitational potential energy at this point right here. And at part C, we've done more. Now we've lost more spring energy and we have more potential energy due to gravity because we're going up the ramp. We're slowing down, less kinetic energy, and then more potential, less kinetic. And then finally at the end, it's all potential energy when we get up to E because we're not moving anymore because we stop at that point and all the spring is not stretched. Write a narrative. Okay, I just really said all of this. So you should pause your camera, take a look. All right, more. Do the energy bar charts depend on whether the cart is moving down the track or up the track? No, doesn't matter. Whether the cart is moving up or down the track, the energy bars will look the same. The total energy should be the same at each labeled point. Why this is the case? Because there's no external forces acting on it. Basically, energy is conserved. So all the little wedgies have to add up to 16. And every position, they all add up to 16. You can see that. The gravitational potential energy should increase by the same amount between each labeled point because the height increase is the same amount. The mass is the same. G is the same. We're going up in even height increments. And when it goes down, it should increase quadratically between each labeled point. The spring energy does, right? Because it's a kx squared type of a deal. And as the x increases, as you go a unit of length down the ramp, whoopsie, there it is. As you go down a unit x down the ramp, between every letter is a unit x, that's squared. So between E and D, that's 1 squared, and then between E and C, that's 2 squared, and then 3 squared, right? And then 4 squared. That's why the spring energy changes exponentially. All right. I forgot to start my timer. I'm sure that's probably enough time. Let's go ahead and stop.